All right, guys. In this video, this is a worksheet for one of the students I tutor. So this is their practice for their Unit 1 test, but it's at a different school. So, but it will help for our Unit 1 test as well. Most of the stuff here is stuff that we talk about in our Unit 1 as well. So let's just go through it, okay? So these are just practice problems for Unit 1 concepts. It's not all the concepts from Unit 1 that we cover at West Springfield High School, but so technically this is for I think Bishop Ireton, but I think all of these concepts we do discuss in Unit 1. We just have a few more things that we do. So make sure you look at our official test review and all that stuff as well, okay? So anyway, let's just dive into it. So I'm going to be a little bit more detailed here as, sorry, I just needed to move where I was so I can control the screen a little bit better. So we're going to go through each of these sections, and I'm going to try to explain some things, hopefully, to help the student I'm tutoring. So I might go a little bit more detailed, not just the answers. So it might be a little bit longer of a video. So just kind of bear with me. Okay, so for significant figures, let's talk about the first section, okay? So remember, when you're just trying to determine if a digit in a number is significant or not, these are the rules, okay? So if it's non-zero, it's significant, okay? It's really just about the zeros. And we classify our zeros three different ways. We'll call them leading zeros. That's zeros to the left of any non-zero digit. When you're looking at the number, leading zeros are on the left-hand side because you lead left to right. So left-hand side is leading zeros. If they're between non-zero digits, we call those captive zeros, and sometimes they may be sandwich zeros. And then if they're zeros to the right of the last non-zero digit, that's what a trailing zero would be called. So you have to define the zero as one of these, and then you got to know the rules. So leading zero is never significant. That's an easy one. And then captive zeros are always significant. That's another easy one. The trailing zeros are where students have the most confusion about, and it's this easy. If you, in the number, you actually visually see the decimal point, then all the trailing zeros are significant. If you do not see the decimal point, you know where the decimal point is, but they just didn't write it on the piece of paper, they didn't type it, then the trailing zeros are not significant. That's the rule, okay? So let's go back and see if we can figure out, or see if we understand the answers here, okay? And so just kind of understand something, okay? So I got some practice here, right? So these would be leading zeros, and we could add a bunch more zeros here. These would be the leading zeros. Why? Because there's zeros to the left of the last non-zero digit, okay? Leading zeros. So these zeros are not significant, okay? This would be an example of a captive zero. And I could have more than one zero in between the 2 and the 6. I could have 2 zeros, 3 zeros, 4 zeros. It doesn't matter how big the sandwich is. It doesn't matter how many captive zeros there are. They're all significant. Okay, so if I had 2 zeros in between the 2 and the 6, that would be 2 significant zeros. Okay, so the 2 is significant, obviously, the 6, and that 0 between them is also significant, so that's why this number has 3 sig figs. Okay, now let's talk about like the trailing zeros, right? So these would be classified as trailing zeros. These would be classified as trailing zeros. The value of this number, 1,000, is the same as the value of this number, 1,000. The difference is how many sig figs, okay? This is 1,000 with only 1 sig fig. This is 1,000 with 4 significant figures, okay? What's the difference? Trailing zeros, and I didn't write the decimal point. Trailing zeros, and I did write the decimal point. So me putting the dot on the piece of paper makes these 3 zeros significant. Not having it there makes these 3 zeros not significant. So 1,000 expressed with 1 sig fig, 1,000 expressed with 4 sig figs. Now, how could you make 1,000 have just 2 sig figs? Well, that's when you would have to say 1.0 times 10 to the third. You'd have to put it in scientific notation to get the correct number of sig digs. Sometimes you have to do that, all right? But anyway, so let's see how we do, all right? So here's our answer key. So this number has 2 sig digs. Why? Well, those are leading zeros, so they're not significant, right? This number also has 2 sig digs. Why are these zeros not significant? Because they are trailing, and I didn't write the decimal. If there was a dot right there, then you would say 4 sig digs, right? But there's not, okay? These would be classified as captive zeros. Why? Because they're in between a 1 and a 3. So all of those zeros would be significant. And then you also have to include the 1 and the 3. So this number, as written, has 5 significant digits, okay? Here, these zeros are not, but these zeros are. The reason why these zeros are is because I have visuals on the decimal point. So they're trailing zeros. They're significant when I see the decimal point. Leading zeros like these are never significant. So this digit, or this number, has 4 sig digs, all right? The zero that's in between the 8 and the 9 would be significant because it's a captive zero. But these 2 zeros would not be significant because they're trailing and I don't see the decimal point. So that's why this number only has 3. Okay? Leading zeros, not significant, so I don't worry about those. That's a trailing zero. I see the decimal point, so that is significant. 3 sig digs. Okay? Here we go. That zero is significant because it's captive. Those 2 zeros are significant because they're trailing and I see the decimal point. So 5 sig digs. This number as written only has 1 sig dig because those are leading zeros, never significant. Okay. All right, so when it comes to doing math with measurements, especially in chemistry, it's going to be the major focus. You have to do your math, and then you have to either report your answer with the correct number of significant figures, or, depending on what you're doing, the correct number of decimal places, okay? So, I think I have it here. Okay, so here's the deal. If you're multiplying and dividing, you limit your answer to the least number of sig figs as the numbers you were using when you were multiplying and dividing, okay? But if you add or subtract, you don't care about sig figs. What you care about is decimal places, okay? So if one number has 2 decimal places and you're adding it to another number that only has 1 decimal place, then you're only allowed 1 decimal place at the end, okay? So usually I say limit, but every once in a while you have to add a digit. But like multiplying or dividing, you're worrying about sig figs. Adding or subtracting, you're worrying about decimal places, okay? So here we're doing math. All we're doing is multiplying and dividing, okay? So when you put this in your calculator, this is what your calculator spits out. But in chemistry, we can't spit that out, right? What we have to do is look at each of the numbers that we used in our mathematical operations. And in this case, since we were only multiplying and dividing, we only care about sig digs. We don't care about decimal places, okay? So what we have to know is this number only has 2 sig digs, this number has 3 sig digs, this number has 3 sig digs, and this number has 4 sig digs, okay? The number that comes out of my calculator has 1, 2, 3, 4, 5, 6, 7 sig digs, okay? Can't do it. Can't report that, okay? So you find the number of all of the measurements of the math you were doing, the one with the least number of sig digs, that's 2 sig digs. So I have to round my final answer to 2 sig digs, okay? So that's what my calculator says, but this is what I report because I'm only allowed 2 significant figures because that measurement only had 2 significant figures, okay? Same thing's holding true here is we're multiplying and we're dividing, so all we're worrying about is sig figs, okay? So we have to understand that this number only has 2, this number has 4, and this number has 3. So my limiting number of sig figs is 2. So this may be what my calculator says, but this is what I got to round to, only 2 significant figures, okay? Now here's kind of a tricky one. This is one where you actually have to add something because you're allowed it, okay? So here we're adding numbers. When we add and or subtract, we worry about decimal places, not SIGDIGs. So here, I have 1 decimal place and I have 1 decimal place. So I'm allowed 1 decimal place. You know, one number might have 1 decimal place and another number might have 5 decimal places. I'm going to have to limit myself to 1 decimal place. Okay? But here's the kicker. When I add these two in my calculator, this is what my calculator says. But you're allowed 1 decimal point. So that's why you would have to add that decimal point. So that would be the correct answer. Okay? Most of the time, you're taking away decimal places when you add or subtract, or you're taking away significant figures when you multiply or divide based on what your calculator says versus what you're allowed to report. But every once in a while, you have to add a digit or two. Okay? All right. So the next section, scientific notation. Okay? The way to think about scientific notation is you're taking a number and then you're multiplying it by 10 this many times. If it's a positive exponent, what this really means is take 3.29 and multiply that by 10, but do it 4 times. So 3.29 times 10 times 10 times 10 times 10. That's all we're doing, okay? But remember, multiplying by 10 means move the decimal point to the right once. Okay, so really all we're doing is taking our decimal point right here. If I want to go from scientific notation to standard notation, I'm taking this and I'm moving it to the right 4 spaces, 4 places on my number line, because if you multiply by 10, you move the decimal place to the right once. Okay. Now, if it's a negative exponent, you're dividing by 10 that many times. You're multiplying by 1 over 10, or dividing by 10, or multiplying by 1/10 that many times. So if it was 3.29 times 10 to the negative 4, if I want to convert that to scientific notation, or sorry, standard notation, I could just take this and divide it by 10 4 times. Here, I could take this, whoops, I didn't know I could do that. Take this and multiply it by 10 4 times. But just like multiplying by 10 means move the decimal place to the right once, and if I want to do it 4 times, dividing by 10 moves the decimal place to the left 1 time. So this really means take the decimal point and move it to the left 4 spaces, 4 times. Okay? That's all it is, right? That's all scientific notation is. Now, proper scientific notation, when you're putting a number into scientific notation properly, there should only be 1 non-zero digit to the left of the decimal. So to get a number from standard notation to scientific notation, you got to move the decimal place so there's only 1 digit to the left of the decimal. Okay? So let's see how we did on the answer key. Okay? And then and another thing, if you have something in scientific notation that's a negative exponent, that means that number is less than 1. So if you put it in standard notation, if it has a negative exponent, it's going to be point something. Okay? If it has a positive exponent, that means that number is greater than 1. You know? Okay? So 3.29 times 10 to the negative 4, I'm going to just take my decimal place, which started here, and I'm going to move it to the left 4 times. Okay? So I start here 1 time, 2 time, 3 time, 4 time. So 10 to the negative 4 doesn't mean add 4 zeros this way. It just means add 4 places this way. So the first place is the 3, and then it would be 3 more zeros. Okay. So here we got 9 times 10 to the third. So they didn't even write the decimal point, but I know where it is. And I'm just going to move it to the right 3 times. So my decimal point was here. I move it to the right 3 times. 9 times 10 to the third, or 9 times 10 times 10 times 10 would end up being 9,000. Same thing. Okay. Here we got 10 to the negative 1. So all I have to do is move that 1 space to the left. So 2.1665 times 10 to the negative 1 becomes 0.21665. Okay. 10 to the 0, that's kind of a trick question. That means just times 1. So it's really this times 1, right? Anything to the 0th power is 1. So it's really just that. Okay. So how do you take a number that's in between 1 and 10 and put it in scientific notation? You keep the number as is, and then you say times 10 to the 0, right? So if we look at this one, right? How do I put that in scientific notation? Well, if it's in between 1 and 10, it's just going to be 10 to the 0 power. Okay. All right, so hopefully, we're getting the scientific notation, okay? Now again, it's proper scientific notation. So for here, right, 32.8 times 10 to the 4th has the same exact value as 3.28 times 10 to the 5th, only this is proper scientific notation. This is scientific notation, it's just not properly formatted, right? You need one digit to the left of the decimal, and this one has 2 digits to the left of the decimal. Right here, we're in scientific notation, but it's not proper scientific notation, okay? So we have to move the decimal place to there, but if I move it to the right 3 times to get to the scientific notation, I'm going to add a -3 to that exponent. So the 10 to the -3 turns into 10 to the -6. Okay. All right, so the next section, just taking a measurement with either like a ruler or a graduated cylinder. So anything that has what we call graduations, tick marks, calibration marks, right? So, here are the graduations of this ruler. Here are the graduations of this ruler. Here are the graduations of this cylinder. That's why it's called a graduated cylinder. Here are the graduations of that cylinder, okay? Whenever you're taking a measurement with an instrument that has graduations, and you're using the graduations, lining up the ruler, reading the meniscus at the graduated cylinder, before you take any measurement, you should know what place your measurements are allowed to be at. Like, so am I only allowed whole numbers? Am I allowed the tenths place? Am I allowed the hundredths place? Am I allowed the thousandths place? And it just depends on the graduations. So the first thing is, when you're taking a measurement, you want to determine what place on a number line, okay, and I'll show you what I mean by that in a second. Hopefully it'll make sense. Each graduation represents. So as I go from this graduation to the next graduation, what is that worth? Okay, and I'm going to show you what I mean in a second, okay? And then if you know what that's worth and where that number is on the number line, you're allowed to estimate one more digit to the right on the number line. So let me show you what I mean, okay? So when we look at this first ruler, right, here's the first graduation, here's the second graduation, the third. So as we go from one graduation to the next graduation, that's an increase in 1 centimeter. So each graduation is worth 1 centimeter, okay? So where does that fit on the number line, okay? That's the ones place. So that means my measurements have to be estimated to the tenths place. So what you just determined there, right, was as soon as you know the graduations are the ones place, that means if I'm using this particular ruler right here, if I'm using this one, here, let me make this a hand just so you can see it better, okay? If I'm using this ruler right here, okay, all of my measurements should have 1 decimal place. It should be to the tenths place. So if I thought this fell right on the line there and I thought it was exactly 4, if I wrote 4 centimeters, I would be incorrect. You need 1 estimated digit. So if it fell right on that line where it says 4, then I should say 4.0 centimeters. But understand, if somebody else said 4.00 centimeters, that would be incorrect for this ruler, because the ruler doesn't allow the hundredths place. This ruler allows the tenths place. Okay? But now if we go to this ruler, each tick mark, each graduation is 0.1 centimeters. So if that is 1, then that next tick mark is 0.1. So if we go back to our number line, the second ruler gives us this place, the tick marks give us this place, the graduations. So that means we have to go to the hundredths place when we estimate, okay? So if I was using this ruler, all my measurements should have a hundredths place. I'm going to estimate that hundredths place. Over here, I'm going to estimate that tenths place. Okay? So, and the same thing's true, it's just here they represent centimeters, and I guess that's a millimeter there, so I guess I got to change the key. Anyway, I thought they were all centimeters. Anyway, whatever. Okay. But here's milliliters, 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 and degrees Celsius. But anyway, this has graduations, this has graduations, this has graduations. So you got to figure out what the graduations give you, and estimate one more place to the right on the number line, right? So if I have the ones place, I can go to the tenths place. If I have the tenths place, I can go to the hundredths place. If I have the hundredths place, I could go to the thousandths place. That's it. Okay. So let's look at this. All right. All right. So I said 3.8. If you said 3.7, you'd be right. If somebody else said 3.9, that'd probably be allowed. Right. It's an estimated digit. Your estimate might not be the same as mine. That's why it's called an estimated digit, but you're only allowed one. What I couldn't do is say 3.80 or 3.81, right? I can't estimate two digits. I can only estimate one digit, right? So 3.8 centimeters. But over here, I think that's right at 4.2, and I think it's right on the money. But I got to remember to say 4.20 or I'm toast. Okay, and again, I thought this said centimeters, so that's why I said 25.5, okay, centimeters. But if it's millimeters, that's fine. It's 25.5 millimeters, okay? Now, the reason I'm allowed the tenths place is because each one represents one, right? So here, this would be 20 millimeters. That would be 21 millimeters, 22, 23, 24, 25, 26, 27, all the way to 30 millimeters. So each tick mark represents 1 millimeter. That's the ones place, so I'm allowed the tenths place. So I need the tenths place. If you thought it was right on the line, then 25.0. Okay. Here again, each one is 0.1 centimeters, so I'm allowed the hundredths place. Okay, and again, this digit is probably good. It might be different than mine. The estimated digit, the last digit to the right of the number, might be different compared to somebody else's because that last digit is an estimated digit. And you only have to worry about estimating digits when it's something that's analog, that has graduations. If you're doing something that's digital, like if you're taking the temperature using a digital thermometer, just write down what the thermometer says, what the digital display says. You don't estimate, okay? Right, but the reason why I'm allowed 8.5 is because each tick mark represents the ones place. I'm allowed to estimate to the tenths place, okay? Here, each one represents 0.1 milliliters. That's why I'm allowed the hundredths place. Each graduation represents 0.1, so I'm allowed the hundredths place. Here, they represent 1, so I'm allowed the tenths place. Here, they go up by, here's 100, here's 200, so here they go up by tens. So that's the tens place. So you're allowed the ones place. So if this is my graduated cylinder, I wouldn't be allowed a tenths place. I wouldn't be allowed a decimal place. It would just be 51 milliliters, right? And remember to read the bottom of the meniscus, okay? Okay, so the next part, again, metric system and SI units. Again, he says metric unit here. I'm guessing he means the SI unit, the International System of Unit. And like on my practice quiz that I give, I say base unit, so that's also kind of a misnomer. So I'm going to assume he means the SI unit, and just make sure, just be careful with mass because that can be made an argument. But the SI unit for all these measurements, for length is meter, so not miles or something. Length is meter. Volume is liter. Okay. Temperature is Kelvin, the Kelvin temperature scale. Time is seconds. Okay, not hours or minutes, but seconds. In mass, the SI unit for mass is actually kilogram. But the base unit of that would be gram, right? Kilo just means 1,000. So kilogram is 1,000 grams. So, but technically the SI unit is kilogram. The base unit would be gram, okay? Okay, so just be careful. I'm not sure if he's asking for the base unit or the SI unit, and I'm usually not a stickler with my students. If I say, what's the SI unit for mass? If you say gram or kilogram, I'll go with it. Just as long as you don't say pounds or something like that, okay? But, yeah, okay. So, so here he's saying complete the following conversion factors. Now, really what he means by conversion factors is equalities. So 1 decimeter equals how many meters? 1 kilogram equals how many grams? 1 milliliter equals how many liters? 1 centimeter equals how many meters? Okay? And from the equality, if you know an equality, you can make 2 ratios, which we call conversion factors. So once I know what value is going to go here, then I could say this many meters over 1 decimeter or 1 decimeter over that many meters. And it just depends on, am I going from decimeters to meters? Which ratio am I going to use? Am I going decimeters to meters or meters to decimeters? Okay. So I kind of have them written down a few different ways. So like you should know that 1 decimeter, deci means 1/10 of something. So a decimeter is 1/10 of a meter. So 1 decimeter equals 0.1 meters. Now, another way to say 0.1 is 10 to the negative 1. Okay. Or you could say 1 over 10. I mean, it's the same thing, right? So you could say that, you could say that, that's an equality, or you could say that, right? Now, the reason why you couldn't say 10 decimeters equals 1 meter on the practice problems is because he locked you in at 1 decimeter. So, right? But if you make that 10 decimeters, if you make that 10, then that's equal to 1 meter. It's all these things mean the same thing mathematically, okay? I'm not sure if he's making you use the powers of 10, if it doesn't really matter to him which way you think of it. But in order to do dimensional analysis with it, in order to do unit conversions with it, you have to have an equality. So you can memorize that, you can memorize that, you can memorize that, but you gotta have that equality, right? So the same thing's true about kilograms and grams, right? So 1 kilogram equals 1,000 grams. Another way to say that is 1 kilogram is 10 to the third, because 10 to the third is just 1,000. Or, right, you could make this 1 gram, and then this would be 0.001 kilograms. That would be the same thing, okay? Right, so milliliters, 1 milliliter equals 1/1000th of a liter, or you could say 10 to the negative third, or you could switch that and say 1 liter is 1,000 milliliters, right? This has the same equality, is the same mathematically as that or as that, okay? So you really need to establish these equalities so that you can use the equalities to make ratios to do your metric conversions, okay? So you can show your work using dimensional analysis, okay? So kind of understand the reason why, so when he says conversion factors, it's really you have an equality that you can make into 2 conversion factors, right? So when we start to convert, when I have 2.5 kilograms, and I want to know how many grams that is, but I need to show my work using dimensional analysis. Well, I have to recall my equality that I memorized. So I know 1,000 grams equals 1 kilogram. And then what I can do is I could use this ratio, or I could use that ratio. What am I doing? I'm taking that and dividing it by that, or I'm taking that and dividing by that. Okay, that's what a conversion factor. So here's a conversion factor, here's a conversion factor. I would use this conversion factor to cancel out kilograms and get to grams. I would use this conversion factor to cancel out grams and get to kilograms, okay? All right. So how would I do that conversion showing my work? Well, I would write my 2.5 kilograms, I would make my T-chart, start my dimensional analysis, and I would use this ratio. Why? Because I need to cancel out kilograms, so 1 kilogram would go on the bottom because I need the units on opposite sides, 1 on the numerator, 1 on the denominator to cancel out. And that would leave me with grams. So mathematically, it's just 2.5 times 1,000. Right? Now, sometimes you might see dimensional analysis set up this way, sometimes with T-charts. It really doesn't matter. You're just taking the number you currently have, so 2.5 kilograms in this case, and you're multiplying it by a ratio. And that ratio is called a conversion factor. It's called a conversion factor because all it does is change the unit. It doesn't change the value. And the reason why it doesn't change the value is because this is a ratio that's made from an equality, right? So I know those two things are equal. So when I take one thing and I divide it by something else that's equal to it, it's really 1. So when I take 2.5 kilograms and I multiply it by this ratio, I'm not multiplying it by 1,000. I'm multiplying it by 1,000 grams and I'm dividing it by 1 kilogram. That cancels out kilogram and gives me grams. But 2,500 grams, which that's what would it be equal to, 2,500 grams, is the same thing as 2.5 kilograms. It's the same thing. We haven't changed the value of the measurement. We've just changed the unit, right? If I give you 2.5 grams of something, that would be the same thing as me giving you 2,500. Or if I give you 2.5 kilograms of something, that's the same thing as me giving you 2,500 grams of something. Okay, so unit conversion is just saying, okay, here's the measurement expressed with this unit. Here's that same measurement with the same value, just expressed in that unit. That's all dimensional analysis is. Okay. And again, it stems from knowing equalities. So memorizing your metric equalities. Okay. So here, like, what if I wanted to go from a centimeter to a kilometer? Well, you could try to figure out how many centimeters are in a kilometer and figure out that equality, but you should, know how to go from centimeters to meters, and you should know how to go from meters to kilometers. So it would just be a 2-step process. Use this ratio, use this equality to make a ratio to cancel out centimeters and get to meters. And then once you have meters, use this ratio to cancel out meters and get to kilometers. So centimeters to meters, meters to kilometers. So we're going to divide by 100 and then we're going to divide by 1,000. Okay. All right. So again, this could be gram if he just wants the base unit for mass. It just really depends on what your teacher wants. So, okay. And I'm sure they probably mentioned that in class. Okay. So here would be the equalities the way it was written. Now, instead of doing the decimals, you could do powers of 10. So this could be 10 to the negative 1. This could be 10 to the third. This could be 10 to the negative 3. This could be 10 to the negative 2. It's all the same thing. Okay. So here, kilogram to gram. Okay. Right. Now notice this one, right? We're trying to maintain significant figures. The metric equalities have infinite sig digs. There's exactly 1 kilogram is equal to exactly 1,000 grams. So that's not going to change my significant figures. So this number has 3 sig digs. So my final answer should have 3 sig digs because all I'm doing is multiplying and dividing. However, this is one of those times where the only way to get the number that of the answer to the right number of sig digs is by using scientific notation. Because 2,500 grams, as written like this, 2 sig digs. If I put the decimal point, 4 sig digs, but I'm only allowed 3, so that's why I have to put it in scientific notation. Okay. So here we're converting deciliters to liters. Okay. Now another way to write this same thing is you could have 1 liter on top and 10 deciliters on the bottom, because 10 deciliters equals 1 liter. But if we're using the equality, basically that we were using here at the beginning, it'd be 0.1 units, 0.1 base units over 1 deci unit. So 0.1 liters over 1 deciliter, right? So I'm just using the equality that they had here. Or you could have 10 to the negative 1. So take this number and multiply by 10 to the negative 1, or times 0.1 is the same thing, okay? So here are the other conversions, right? Meter to kilometer, I divide by 1,000, but this is showing how the meters cancel out and you're left with kilometers, right? So here I'm going from centi to kilo, all right? So first I'm going from centi to the base unit meter, and then meter to kilometer, okay? So multiplying by 0.01 is the same thing as dividing by 100. So take this and multiply by 0.01 or divide by 100, and then divide it by 1,000, okay? All right, this one's kind of a trick question. You should memorize that a milliliter is the same exact thing as a centimeter cubed. That is what a milliliter is. It's a centimeter by a centimeter by a centimeter. So it's a little cube that's a centimeter wide, a centimeter long, and a centimeter tall. That's what a centimeter cubed is, and that is the definition of a milliliter. Okay? And so if you want to actually show it in dimensional analysis, you can say 1 centimeter cubed is equal to 1 milliliter, and you can make a ratio to cancel out milliliters and get to centimeters cubed, but you're just multiplying by 1 and dividing by 1, so it's the same exact number. Okay. You should also memorize that a liter, 1 liter, is the same thing as a decimeter cubed. So a decimeter cubed is the same thing, the same exact thing as a liter, and a centimeter cubed is the same exact thing as a milliliter. Okay. Okay, so for the last practice problem here, they give us information, and we're going to use the data collected in the lab to identify the metal, okay, by determining the metal's density. All right. So density is mass divided by volume. And one way to figure out volume, especially if you have like, you know, a rectangle box or a cube, you can just do length times width times height. So we have the length, we have the width, we have the height. So length times width times height. If I do this times this times this, that'll give me my volume. I have my mass. Mass divided by volume gives me my density. Once I have my density, whichever one is closest to, that's what I'll guess what metal I have, right? Okay. So let's think about sig digs, right? So to get my volume, I'm multiplying those distance values together, length times width times height. So centimeter times centimeter times centimeter, my units are centimeters cubed, which is a volume. And because each of my length measurements have 3 sig digs and I'm multiplying, I should round my answer to 3 sig digs. So 6.11 comes out to be the answer, and it's centimeters cubed. Okay. Now density equals mass over volume. So I'm going to take the mass measurement they gave me. I'm going to take the volume measurement that I calculated, and I should round to 3 sig digs. The reason that is the mass has 4, but the volume I'm using only has 3, so I should round to 3 sig digs. And then that's my density, and that's the same as the density as copper, so I think my unknown metal is copper. Okay. And then here, using the density equation and or dimensional analysis, to go from volume to grams, or grams to volume, right? So here's your volume of your titanium ball. You're given the density of titanium. You want to figure out the mass of your ball. So D equals M over V, but we're solving for mass. So mass equals density times volume. So all you have to do is plug in your density, which was given to you here, plug in your volume, which was given you here. As long as the units match, the units have to match. So centimeters cubed cancel out, and you're left with grams. We're rounding to 3 sig digs because my volume had 3 and my density had 3. So my final answer here has to be limited to 3. Okay. Now, we could take the same question and use dimensional analysis. Okay. We should interpret density. We should understand that density is our conversion factor to go from mass to volume, or in this case, volume to mass. Okay. So if I want to show my work using dimensional analysis, the way you should think about this density is treat it like it's an equality, and from an equality you can make the 2 conversion factors. So what we're saying is 4.5 grams of titanium is equal to 1 centimeter cubed of titanium. So if I take my centimeters cubed that I was given, and then I multiply by this ratio, 4.5 grams over 1 centimeter cubed. Centimeters cubed cancel out. You're left with grams. Okay, you do this times this divided by that. You end up with 157.5. You round to 158 because you're only allowed 3 sig digs. Okay. So again, what we did there was look at the density, interpret it as an equality, and now these are the 2 ratios, these are the 2 conversion factors that I get from given that density. So given the density, I know that that equals that, and then anytime I have an equality, I could say 4.5 grams over 1 centimeter cubed, or I could say 1 centimeter cubed over 4.5 grams. So what if I was given mass and I wanted the volume? Okay. So if I had 25 grams of titanium and I wanted to know the volume, right? I'm going to start with my 25 grams, but then I would use this ratio. Why? Because I need grams to cancel out, and I want to be left with the volume, centimeters cubed. And remember, it's the same thing as milliliters, so you could rewrite this as milliliters. It's the same exact thing. But here, because my mass only had 2 sig digs, that's why I rounded my final answer here to 2 sig figs. Okay, so that's just, using density as a conversion from mass to volume, or using density as a conversion from volume to mass. Okay. All right, so I hope that helps you out preparing for your Unit 1 test over there at Bishop Ireton. And those of you that are at West Springfield, if the video was beneficial to you, good luck on your Unit 1 test. Okay.